and I've got, say, that loose end here with string like that, I do get an antinode right there. That's really an antinode. That's a big, fat, biggest vibration right there at the end of the string. What's really uncomfortable with the tube is when I look at an open tube like this, whether it's open or closed at one end. At the open end, the antinode is not going to be exactly here. The antinode's actually outside of the tube a little bit. Now, you did a little fake little approximation in lab that we actually screwed together just by doing a lot of experiments and trying to get a number for it. But actually finding out where the antinode is for an open-ended tube is a phenomenally difficult differential equation. It actually depends on the speed of sound, depends on the size, depends on the shape, depends on the frequency. So where the antinode actually really is really, really difficult for the tube. The other thing is when I talk about an antinode of what? If you look at a tube, I can try to describe the particles in the tube in two nice ways. If I get a tube like this, just make it easy like that. I can look at the pressure on the particles. I can look at the pressure. And if the pressure is really great, the particles can't move very much. Or I can look at the amplitude of the particles, how much they move. I think it's better to deal with the amplitude deal as opposed to the pressure. Most books will just do this. And the reason they do is because when you look at this, it looks exactly like strings, which is really nice for people. If you look at pressure, it's like the reverse of the amplitude. For example, I got this tube, it's open at both ends. Okay, when it's in resonance, I get a minimum pressure here. I get a minimum pressure, which means the particles can scream out like crazy, and there's very low pressure there. And then I move into the place which you would consider in terms of the strings as the first node. Right in here, I get a lot of pressure. I get high pressure, and the particles can't move very much. Their amplitude is very, very, very small, and it continues like that all the way down to here. I go from low pressure, where the particles move around a lot, to high pressure, where the particles really can't move. I get another antinode right here, antinode, low pressure, big movement in the particles. And what this book does is he tries to treat these both equally. I don't want to deal with the pressure. It's not, the pressure is kind of cool. Because, yeah, the pressure does change. If you put a little gauge, if you put a gauge in this thing, and put a gauge and read the pressure right here, it would be relatively low here. At this point, the pressure would be higher. You'd actually see the pressure higher at that spot. If you came up to the next antinode, it would actually read a low pressure. If I had a little gauge, it was actually reading pressure. There would be a difference in the pressure along here. Pressure would actually be different. But like I said, I'd really rather prefer to deal with the amplitude because it just looks more like strings. It's usually easier for people to deal with. So that's why I'm going to do the amplitude. If you're worried about the pressure, you just kind of say, well, the pressure is the reverse of what the amplitude is. So if I know where I get a big amplitude, that's where low pressure is going to be. And if I get a really tiny amplitude, that's the place where I'm going to have a high pressure. But like I said, I'm not going to bug you about that because I think it looks easier to deal with this just in terms of the amplitude, really the displacement. They'll call this the amplitude or they'll call it the displacement because the particle's displacement, or the right spoke displacement, that's where the particles really are allowed to shake the biggest distance. That's why they'll call it the amplitude. So if I look at a tube, and yeah, I'm going to do this one. That's probably going to be it. And I'm going to look at a tube, and actually, I'm going to do this back. No, I'm going to do this way. And I hate doing it this way, but it'll make Yeah, let me do a tube that's like closed at both ends like this. So it's closed at both ends. Now I can shake this somehow, whether I got, it's like a whistle and I got some sort of opening, I'm driving it somehow, but I could get some sort of resonance pattern in there. Okay, it's a little bit like a flute. Let me draw a little bit bigger. No, you know what? I'm going to open it. That looks better to people. Open it like this. Look at the open ends like that. and an open-ended tube, which weird is what I was going to do, the closed-ended tube, is exactly the same. And that's really weird, but it does work out exactly the same. If I look at this thing, I know if I just look at, like I said, I'm just looking at the amplitude or the displacements. I get a maximum here, and I'm going to draw a maximum like this. So you kind of say, wait a minute, it's not a string, it's a displacement. But I'm going to draw it big like this, because that really indicates that, yeah, I got my maximum amount of displacement here, or I got my maximum amount of displacement here. For example, if this was a node, I would have a minimum amount of displacement. This really represents the fact that the particles can shake up and down. So it looks like I'm drawing strings on the picture, but when I draw the picture inside here, the string big amplitude, that means I have a lot of displacement, a lot of place for these things to move in. So I could do a bunch of, nodes and stuff like this in here, and I could have some sort of function where, right here would be a node, this would be an antinode, this would be an antinode. So how can I use that to get an equation? Like I said, this should look really, really similar to what we did with string. I go, okay, my first possible resonance pattern, and I'm ignoring the fact that the antinode's actually outside of the tube, just to make my life simpler. It's not much, but it is outside the tube. You should have seen that in the lab. Like I said, this is fake. It's fake, but it's a nice first approximation. I could say, you know what? In my very first resonance pattern, because I know the open end has to be an antinode, and I know this open end has to be an antinode, I get what looks like, well, I know from a node to an antinode it's a quarter wave. That's quarter wave. So in this case, the length of the tube really has to be, well, 2 quarter waves. That's just lambda over 2. My very next resonance is going to look something like this. Okay, and I look at it and I go, hey, I got a quarter wave here, I got a quarter wave here, and I got a half wave here, and that looks like, well, there's a half wave plus I get another half wave. And you can kind of guess that each time I go to the next resonance, I'm just adding on another half wave. If I look at the next one, my very next resonance pattern, as far as the displacement would go, would look something like, oh, did I get that right? No, I put in too many bumps. The very next resonance is going to look something like that. Bad drawing. But you look at it and you say, I got a quarter wave here, I got a quarter wave here. So that's my grand total half wave sitting out in front. But then I get another half wave here and another half wave here. So that's really just another half wave plus another half wave. And I can say, looking at my pattern, I can go, well, when I go from one resonance to the next, I'm just adding on half wave. So the length of my tube has got to be equal to an integer number of half waves. And you should look at that and say, hey, that's the exact same thing you had for a string tied at both ends. And that's the point of doing the strings, is that the math is very, very, very similar. So I could say, once again, I know that the frequency times wavelength has to be velocity. So the wavelength equals velocity divided by the frequency. So I get the length of the tube is n times v over 2f. Multiply both sides by f, divide both sides by l. And I get the resonance frequencies are going to be nv over 2l. Which you would say, man, that's the exact same thing as a string tied at both ends. It is the exact same thing as a string tied at both ends. Once again, no, it's not, because actually the node's a little bit outside of the tube. But we kind of fudge that and ignore that for right now. Okay, like I say, you should have seen it loud, but I'm going to pretend, yeah, the end of the tube is an antinode. What's interesting is, and if you want to try this, if I looked at a tube that was closed at both ends, I would get this pattern. And then if I look at the next one that was closed at both ends, the very next one, and you're going to say, wait a minute, that's just adding a half wave on each time. The very next one's going to look something like this. And the very next one would look something like this. And you'd say, mathematically, that's the same. A tube that's closed at both ends behaves exactly like a tube that's open at both ends. We almost never do the tubes that are closed at both ends because it kind of confuses people. But it is the same as a tube that's open at both ends, which is really kind of weird. I'm going to do a lot more stuff with this sound stuff on Friday. I won't